All right, let's jump right in. Today, we're going to talk about a concept that's quietly running the show behind so many things you use every day, from the undo button in your text editor to your browser's back button. It's called the stack. And the cool thing is, even though it's a huge deal in computer science, the basic idea is something you already get intuitively.
Yeah, seriously. To get your head around a stack, just think about a stack of plates sitting by the sink. When you add a clean plate, where does it go? Right on top. And when you need a plate, which one do you grab? The top one, of course. You're not going to try and wiggle one out from the middle of the pile, right? That would be a mess. Well, that simple, obvious action, that's the entire secret behind the stack.
And this idea, well, it has a fancy name, LIFO. It stands for last in, first out. The last plate you put on is the first one you take off. This is the golden rule, the one and only unbreakable law of the stack. So burn that acronym into your brain, LIFO, because everything else we talk about comes back to this one simple principle. Okay, so we've got our plate stacking rule. Now, how do we take that real-world concept and teach it to a computer? How do we make sure our code follows that rule? Well, it all boils down to one simple constraint: controlling exactly where we can touch the data. Think about those plates again. You only ever interact with the top of the stack. A data stack is exactly the same. There is only one place you're allowed to work, and we call that spot the top. It doesn't matter if you're adding something, taking something away, or just looking, you have to do it at the top. No exceptions. So now that we know the big rule, only touch the top, let's talk about what we can actually do. In programming, we call these actions operations. And the beautiful thing about a stack is its simplicity. You don't need a huge instruction manual. There are really just 3 basic moves to master. And here they are. First up is push. That's just our word for putting a new plate on top of the stack. Next, we have pop. You guessed it, that's taking the top plate off. And finally, there's peek. Peeking is like glancing at the top plate to see its design, but without actually picking it up. Push, pop, and peek. That's the whole toolkit. Okay, theory is great, but how do we actually make this happen? How do we tell a computer to follow these rules? Let's get our hands dirty and see how we can build a stack from the ground up using C++ and a good old-fashioned array. So here's our basic blueprint. At its heart, we're just using an array to store the items. But the secret sauce, the real brain of the operation, is this little integer variable called top. Its only job is to keep track of where the top of our stack is. And notice how we started off at -1? That's a classic trick. Since arrays count from 0, setting top to -1 is our clever signal that, hey, this stack is totally empty right now. Now, before we write the code for our moves, we got to think about what could go wrong. There are 2 classic problems. First, what if our array is completely full and we try to push one more thing on? That's a stack overflow. And on the flip side, what if the stack is empty and we try to pop something off? That's a stack underflow. Any good stack implementation needs to watch out for these 2 scenarios. Let's look at the push operation. You can see the very first thing we do is that safety check. The if statement makes sure we're not overflowing. Assuming we've got room, the magic happens in 2 quick steps. First, we increase top by 1, so it points to the new open spot. Then, we just drop our new value into that spot in the array. That's it. Simple, clean, and efficient. And here's what that actually looks like. If our stack was empty, top was at -1. When we call push 10, top moves up to 0, and we place the number 10 right there. Our top variable is now pointing squarely at the newest member of our stack. Now, if you thought push was simple, get a load of pop. It's even more slick. First, our safety check for underflow. If we're good to go, if the stack actually has something in it, all we do is decrease top by 1. That's it. Notice we don't bother erasing the old number. We don't need to. By just moving the top pointer back, we've basically said that spot doesn't count anymore. It's a super fast way to remove something. So let's say we had pushed 10, then 20, then 30. Our top pointer would be sitting at the index holding 30. When we call pop, the top pointer just moves back 1 step to point at 20. Now, the number 30 is still technically sitting there in memory, but for all intents and purposes, as far as our stack is concerned, it's gone. The only thing that defines what's in the stack is where that top pointer is. And finally, we have our peek operation. You can think of this as window shopping. We want to see what's on top, but we don't want to buy it, or in this case, remove it. So again, we check if the stack is empty. If it's not, we just return whatever value is in the array at the location top is currently pointing to. We get the info we need, and the stack remains completely unchanged. All right, so we've built the individual components. We have our data structure, and we have our 3 key moves: push, pop, and peek. Now let's put it all together and watch this thing come to life in an actual program. Okay, check this out. Here in our main program, you can see the LIFO rule playing out perfectly. We create our stack, we push 10, then we push 20, and then we push 30. So what's at the top right now? The last one in, which is 30. Our peek function would tell us exactly that. Now, what happens when we pop? That 30 gets removed. And if we check again, the new top is 20. See? It just works every single time. Last in, first out. So you might be thinking, okay, that's a neat little programming trick, but why did we spend all this time on it? Well, because this simple, elegant data structure is an absolute workhorse. It's hiding in plain sight, powering some of the most common software features you use every single day. Ever hit Control-Z to undo a mistake? That's a stack. Every action you take gets pushed onto the stack, and undo just pops the last action right off. That back button in your web browser? It's just popping pages off a stack. But even deeper than that, the very way a computer program runs, how it keeps track of which function called which function, that's all managed by a critical system called the call stack. It is truly one of the most fundamental concepts in all of computing. And here's the real kicker. The reason stacks are so popular? They are ridiculously fast. In computer science, we have this thing called time complexity to measure efficiency. All you need to know is that for a stack, all 3 of our main operations, push, pop, and peek, take what's called constant time, or O of 1. This means it doesn't matter if your stack has 10 items or 10 million items. The time it takes to grab something from the top is always the same. It's predictably, reliably, and incredibly quick. So, to wrap it all up, the stack is a simple, elegant, and blazing fast tool. It's all built on that one powerful rule: last in, first out. It is without a doubt one of the most important building blocks in a programmer's toolkit, running silently behind the scenes to make so much of our digital world possible. So I'll leave you with a question. Now that you know the LIFO rule, start looking for it. Think about your everyday life: a Pez dispenser, a pile of magazines you mean to read. Where else do you see this simple, powerful idea of last in, first out at work all around you?